In this video, we'll learn about Bronsted-Lowry acidity through the quantitative perspective. Before we get into Bronsted-Lowry and the quantitative perspective, we first need to look at some definitions about acids and bases. The idea of acids is that they are solutions containing lots of H pluses or protons, and bases are solutions that contain lots of hydroxides or OH minus. This idea and this definition of acids and bases is not very useful when we talk about organic chemistry. Since we do not tend to do our reactions in water, we do not have an aqueous solution that can readily create H pluses or OH minuses. Instead, we tend to look at acids and bases through the Bronsted-Lowry theory, which defines an acid and base based on what happens during the chemical reaction. And so any reaction that transfers an H plus or a proton from one molecule to another is classified as an acid-base reaction. So we can really boil down the Bronsted-Lowry acid-base reactions as their single proton transfer process. So all we're doing is moving a proton from one molecule to the next, and that would be considered a Bronsted-Lowry acid-base reaction, which becomes a much more useful definition when we're looking at organic chemistry. Now, when we're looking at a Bronsted-Lowry acid, Bronsted-Lowry acids are substances that donate a hydrogen ion, so they donate the H plus. The Bronsted-Lowry base is a substance that accepts the H plus. And we tend to write H plus, and we just call it proton, because we can think of H plus. If we have hydrogen, the loss of a valence electron from the hydrogen gives just the nucleus, which is a proton. So when we write H plus, we're really just writing proton. So if we look at a couple different acid-base reactions down here, I can see I have HCl. HCl has a chlorine and a hydrogen, and then we have water. What will happen is the lone pair from the oxygen on water is going to bind to the H plus, which will leave us with a chloride minus and a hydronium, H3O plus. So you can see that hydrogen is now on the water molecule. We transferred the hydrogen over. You can also see water acts as an acid. So here we have ammonia, NH3. Its lone pair is going to bind to the hydrogen of water, which will give us ammonium, NH4, and hydroxide, OH minus. So you can see the hydrogen got transferred from water over to the ammonia, which again is another acid-base reaction. And if we remember our acid-base reactions in the Bronsted-Lowry definition, most acid-base reactions are reversible. So therefore, we also have to talk about the conjugate acid and conjugate base. So when the base accepts a proton, it becomes a conjugate acid. When the acid donates a proton, it becomes a conjugate base. Hopefully you are familiar with these definitions from general chemistry. But we can look at our reaction here. Our base always turns into our conjugate acid. Our acid always turns into our conjugate base. And so if we did the reaction in reverse, NH4 here, that would act as an acid and donate the proton to the hydroxide. And then now looking a little bit more at the math behind it. When we talk about Bronsted-Lowry acidity, we usually talk about Ka, or the acidity constant. And so a specific equilibrium constant for acid dissociation only includes the species which concentration changes. If we remember, the concentration of water does not change in the course of a reaction, so we can get rid of the water here. So that means Ka, our acid constant, which is a measure of our acid strength, is really the concentration of hydronium times the concentration of the base divided by the concentration of the acid. So this means for stronger weak acids, remember we use Ka when we're looking at what's considered a weak acid. So for the stronger of our weak acids, they'll have a higher percent ionization, so more of it will turn. So more of those acid molecules will lose their hydrogens, which gives us a higher H3O plus concentration, which means we have a larger Ka. So the stronger the acid, the larger the Ka. But looking at different Kas, that's not really useful. And the numbers tend to become really large or really small, and they don't mean as much. So another way we can look at our acid-base strength is to look at the pKa. So our acid strengths are normally expressed in pKa's, which are much easier to convey back and forth to each other. So remember, pKa is the negative common log of a Ka, just like how a pH is a negative common log of the hydronium concentration. So our pKa equals negative log of Ka. And so that means for our stronger acids, they'll have a smaller pKa. So you can think larger Ka equals a smaller pKa. So strong acids, smaller pKa's. Weak acids, larger pKa's. And we tend to use our pKa values in organic chemistry, and you'll see that from your table of pKa's for the different functional groups. And so this definition becomes much more useful when we're looking at our acid-base reactions and we're looking at our reactions with organic chemistry. If we know the rules about acid-base reactions involving pKa's, we can tell if a reaction will occur or not without having to think about it too much. And so if we look at that idea, the pKa predicts the position of the equilibrium. Equilibrium will always favor the weaker acid, or will always favor the higher pKa value. So that means in our reaction here between acetic acid, which has a pKa, so that means looking at our reaction here between acetic acid and hydroxide, acetic acid has a pKa of 4.6 or 4.76. Our conjugate acid on the other side, water, has a pKa of 15.7. What that means, water is a weaker acid than acetic acid because it has a higher pKa. So that means when we're thinking about the position of the equilibrium, it's going to favor the formation of that weaker acid. So the equilibrium is going to fall towards the products and favor the products. Just a little bit goes back towards the reactants. But if we know our pKa values and we look at our pKa tables, that's how we can learn our pKa values. We can determine the position of the equilibrium for our reactions. And so this gives you guys a brief review of Bronsted Lowry acidity and pKa's. So remember with our pKa's, we look at the values of them to determine where the equilibrium lies. You always look at the pK of the acid and of the conjugate acid. And the equilibrium will always favor the formation of the weaker acid, will always favor the side with the higher pKa.